Hey guys, this is another one of Mr. Martin's math and physics videos. This is for British Columbia Physics 12. I actually just made a video here with all of these annotations, but my screen recording didn't work, and so I'm doing this again, but this will be an abridged video, but we will try to go over all of the points still. All right, so here we're looking at electrical field strength. We'll be spending two separate classes on this. So on Thursday, we're going to cover more on this. But this first part I want you guys to have done before Thursday. So what is a field? An electrical field is a region of space in which a charged object is acted upon by a force. The electrical field shows the direction that a small positive test charge would move in a region of electrical field. So here, this is a diagram of a positive test charge's electrical field and a negative test charge's electrical field. Note the direction of the arrows around each charge. And so the reason why the arrows move away from a positive charge and towards the source of the charge and the negative charge is because the arrow direction is based on a positive test charge. That's why I put a box and underlined it several times here. So if you were to put that highlighted positive test charge in a positive field, it would be repelled because they're like charges. And if you were to put that same positive test charge in an electrical field, a negatively sourced electrical field, it would move towards the negative charge. That's why the arrows are moving towards the charge. Okay, same thing if you have more than one charge creating the field. So here the fields are interacting with each other. If I were to put the positive test charge way over here, that the positive source charge would be repelling that test charge, but the negative one would be kind of pulling it towards itself, but not as much as it's being repelled. So that's why you have this kind of curved upwards. Whereas if you put another positive test charge between the two, it's going to get pulled by the negative source charge and repelled by the positive charge. And so both of them are pushing that positive test charge in the same direction, being to the right. Okay, now if both of them are the same here, okay, in this situation, what you end up with is, so if you have a positive test charge up here, both of the source charges are pushing that positive test charge away. Okay, now here, the reason why that test charge in this situation isn't impacting the shape of the electrical field in these diagrams is because the positive test charge is a small positive test charge, and the effects on the electrical field itself are negligible. Okay, whereas here, these two sources of the field are not negligible. That's why the field shape changes, but the test charge doesn't affect the shape of the field. Okay, same thing over here. The magnitude of these two charges is similar, so the field is changed by their interaction, but the positive test charge over here is so much smaller that it's not going to impact the shape of the overall field that it's in. Okay, and in this situation, both of them are repelling that first charge. In this situation where the test charge is in the middle, it's going to get either pushed up or pushed down, right? Because it can't go left, it can't go right because it's being repelled on both sides, so it's going to kind of overflow either up or down to get out of there, that awkward situation. Okay, you also have situations like this where you don't have a single point producing electrical field, but you have kind of these plates, and so, but it's the same idea here. If you were to put a positive charge in between them, it would get pushed away from the positive side and attracted to the negative side. Okay, so the first part of your assignment for this 6.3 section, specifically the first part of our work on this section together, is this quick check where you're going to go on page 173, and there's some diagrams based on celery seeds and their interaction in electrical fields. And so based on those diagrams, I want you guys to draw these types of diagrams of electrical fields. Either this, if there's just one charge, or these kinds of diagrams if there's 2-point charges or two plates, like in the very bottom there. So you have to make those diagrams and also answer the next two questions here. Here for number 3, just keep in mind to see what happens to the vinyl when it's rubbed to the fur. and to the strip of glass when it's rubbed to the wool. Just go back to 6.1, that continuum of electronegativity that shows where electrons kind of jump to and from when two substances interact and are rubbed together. Okay. Now let's actually put some math in here. So now we're going to define and calculate and measure this electrical field strength. Okay, it's very similar in a lot of ways to gravitational field strength. So that's a parallel that's going to show up a lot. The E here stands for the electrical field strength. That's what that E represents. Fe we know is force, electrostatic force. Okay, and Q is the charge. Now here Q, it's specifically Q2 in your textbook. That subscript, the subscript 2 here does not show up in the textbook, but it should, because here you're dealing with not the charge of the charge that's creating the field. You're dealing with the charge that's being influenced by the field, not creating the electrical field. Okay, so it's Q2 you're wanting to put in there, the value of the test charge, and not the value of the source charge is your denominator in this equation. Okay, just like if you were to take gravitational field strength, looks like this, right? You take this equation, you just rearrange it, you get this, where little g is that gravitational field strength. All right, and it's force gravity divided by the mass, but this mass is not the mass of the Earth that's creating the gravitational field. It's the mass of the human on the surface of the Earth that's experiencing the field. Okay. Even though the human's creating a small gravitational field, also it's negligible in comparison to the Earth's gravitational field. So the human is like, in essence, the test mass, like the test charge would be in electrical fields. Okay, so there's that parallel there. Okay, so with this equation, all right, and the units of E here are N over C, newtons per coulomb. So you're going to experience 1 newton of force, or this amount of newtons of force for every 1 coulomb of charge of the test charge that's entering your electrical field strength. Okay, your electrical field. So those are the units of E. All right, so on page 175, you have this practice problem. I did one of here where just looking at the question, we determined that we were trying to solve for the charge of the test charge experiencing the field, and we had the force it experienced and the value, the strength of the electrical field given to us in the question. All right, and then we just had to rearrange our equation, plug those values into the equation, plug and chug, and then we get our answer, which was 4.5 times 10 to the negative 5 coulombs. Okay, the next 2 questions here are for you to do for your homework on page 175. They're essentially just giving you 2 of the 3 variables in our equation. Then you have to solve for the 3rd variable. Very straightforward type questions. Okay, now for this next section here, we come up with a second equation for electrical field strength, right? Because when we go back to gravitational field strength, you'll remember the gravitational field strength actually had 2 equations. Yes, it's equal to force gravity divided by the mass of the object, okay? But it's also equal to this here, right? And if you remember how we got this equation for gravitational field strength G, it's down here, kind of the proof, where Fg is equal to m times G, and then the m's cancel out to give us this equation over here, okay? So we were able to measure the gravitational field strength both with this equation and this equation. So it's the same thing with electrical field strength. We're going to be able to measure it with this equation, but also this equation here. And the way that we get this equation is we combine it with our Coulomb's law equation for electrostatic force, which I did here, and then you cancel out the Q2s, okay? And then you're left with Q1. Now here in the original notes, for some reason, there was a 2 in the subscript there. It should be a 1, okay? It is a 1 in your textbook, so that's good, that's correct, though it's not in your formula sheet, so if you want, you can add that to your formula sheet. But now, this equation doesn't use the test charge like this equation here. It doesn't use Q2, it uses Q1, okay? Just like gravitational field strength here, the second equation didn't use the mass of the person or the object on Earth. It used the mass of the Earth to determine the electrical field strength, gravitational field strength. Here, it uses the charge of the source of the electrical field to solve for the electrical field strength. Okay? And then again, on page 176, you have some questions similar to page 175, looking at some applications to this. I answered the first one, again, just a plug and chug question. I have my original equation with Q1. Here they're asking me for electrical field strength when you have a distance of this, and this being my source charge, that Q1 for this particular electrical field. Plug and chug, you get your answer. Okay? Number 2 and 3 are your homework for this again. So your homework again for due Thursday is going to be page 173, 174, this quick check. All right, questions 1, 2, 3. Questions 2 and 3 on page 175, and questions 2 and 3 on page 176. All right, let me know if you have any questions in the comments or in the homework questions channel in Teams, and we'll see you next time. Goodbye.